Hello and good day to you. So if you want to follow along today, you're going to need the libraries ggplot2, glmnet, so Golf Lima Mike November Echo Tango, TDIA, so Tango India Delta Yankee Romeo, and the library mass, all capitals, Mike Alpha Sierra Sierra. So if you're looking in front of you, you can see the function getResults, which takes two variables and creates a bunch of random data, and performs two regressions of ridge regression and lasso regression, and a standard regression just for comparison. And then it gives me the data to plot to show you the effects, but also we'll do this cv.glmnet cv lasso. It's called the variable is called cv lasso, but the function is called cv glmnet, and that produces this graph over here with these lines indicating the suggested lambda that you should be using in your data, which, if you notice, is a function up here and is taken as a variable into the glmnet that run the ridge function, the ridge regression here, and you can tell it's a ridge regression because the alpha is 0, and same again for the lasso regression where the alpha is 1. Now, I struggled with ridge and lasso regression because I feel it's very badly taught in the textbooks. If you go to your textbook, you will see something that says this, that ridge and lasso regression is useful for dealing with data that has a large amounts of multicollinearity and covariance. Now, it's not that I don't understand that, it's that it didn't really make sense why you wouldn't remove variables that have collinearity and covariance like a sensible person. There's lots of functions to do that. We've already covered it on this channel. Though I found a better explanation which I feel is absolutely superior, and I wish to go through first. So lasso and ridge regression is useful for malposed questions, and malposed questions are the opposite of mathematically well-posed questions. A well-posed question, the solution exists, the solution is unique, the solution's behavior changes continuously with the initial conditions. If you think a solution exists, if you've got loads of variables which have nothing to do with your data, they are going to cause problems. And you can liken this back to the metaphorically to the standard algebraic nonsense of 4 plus s equals 9 plus s, because when you subtract x from both sides you end up 4 equals 9, and that is actually probably closer to what you're doing if you're including variables that have no reason to be in your data, and we'll show you an example of that by the end. The solution needs to be unique. You don't need, if you end up with two possible answers to the same question, you're going to have covariance and collinearity, and that's going to cause problems. And I like to think of that as simple and beautiful solutions are better, and I think of this as E equals mc squared, has only a few variables and yet can describe huge amounts of information about the real world. And this is what you should be aiming for with your regression, that you should be aiming for as small a model as possible. Complex models overfit, and we'll get to overfitting in a second. But the last bit is the solution behavior changes continuously with initial conditions. And that to me is just saying you're still doing linear regression. If you're doing non-linear regression, you need to do something a bit more complicated. A non-unique solution leads to overdetermined or underdetermined data, and this will be your overfitting. And overfitting is where your model, rather than learning the actual underlying algebra and stuff that you're trying to get at, is learning the random noise within the data. And when you've got an overfitted model, its predictions are not reliable, and they're not reliable on unseen data because it's included all this random noise into its decisions. So what we prefer, if we've got an overfitting model because it's too complicated, is for our regression to produce smaller coefficients, and Ridge and Lasso do this by offsetting the way it learns. Lasso will turn covaried values, pick one and turn it into a 0, and Ridge will just penalise them and make them much smaller, and that will hopefully stop it overfitting. Now, going back, in the perfect world, you'd like to have your simple, beautiful mathematical equation that's like 2 or 3 variables and yet predicts everything that's going on. But the real world is you're going to struggle to find that through all the possible combinations and variables within your data. And so where Ridge and Lasso regression comes in is for making one of those unwell posed questions answerable, and creating a model despite there being a little bit of covariance or collinearity involved, or despite the fact you haven't identified all the possible variables to drop. Now, going back to the function you see in front of you, just as a quick explanation of how it runs, produces 5 variables, helpfully named v1, v2, v3, v4, v5, and v2 is covaried with v1, and v4 is covaried with v3, and as you can see how we've managed that. And these are all randomly produced, and it randomly produce a residual, and the y value includes all the values 1, 2, 3, 4, 5, and the residuals. Now, the 3 linear regressions, as you can see here, coefficients linear model, coefficients Ridge regression, and coefficients Lasso are here, and they're both taking in a value of lambda that's taken in when you run the model. And the Ridge regression is produced with alpha 0 and the Lasso by alpha 1. It then constructs a frame including the coefficients, and this can show you how these different models handle their coefficients and how they produce them from random input data. Finally produces a coefficients total of the 3 frames of data, and will then print out this, which will give you an idea of where your lambda should be, and it's a log value, so you may need to do a little bit of translating from that. But we'll also print out a couple of variables for you to look at. Now, first of all, I'm going to do that. Copy and pasted wrong. First of all, I'm going to do this, and I'm going to create a variable called g, which runs the function and produces 1,000 variables. 1,000 runs the process 1,000 times to produce 1,000 instances of the linear regression, the Ridge regression, and the Lasso. Now this goes off the page, so it's not exactly as useful as we'd like. But I'll rerun it in a second to show you how Ridge and Lasso differ. If I run a box plot, you'll see that both Lasso and Ridge have got rid of the v4, which was covaried heavily, and you can see that both of them, in both cases, their handle, they're smaller on each of the variables than the linear regression. Now, linear regression is the only one that seems to spot that v5 is not correlated. So this is one reason why you don't want to throw in Lasso and Ridge regression where you've got nonsense variables in your data. But it can be a first spot of removing some things like your v4, because as you'll notice when I run this again and I only produce it 5 times rather than 1,000, I'm just going to go back, bring that back up again. For v5, linear regression manages to get it into a minus number, which is still not perfectly helpful because that variable is is problematic. But if we look at the lasso is much more likely to get V4, manage it down to a 0, and you can sort of see for where there was covariance in the data, the ridge and lasso has done much better in managing it and coming up with a contracted or compact variance at the expense of maybe some error. So I hope that's useful. I feel that ridge and lasso regression are both useful when you've got malposed questions. So you know, that at first made me scared of them, because I sat there thinking, well, I don't want a malposed question, I want to understand the question properly. But hopefully you can see this is one method of looking at your data in a different way. Lasso in particular, because it forces a lot of variables to 0 when they have covariance, is useful, even more useful than stepwise regression techniques, in cutting out a lot of covaried variances at the very first instance, so you're not continuing looking at them moving forwards. So one way to look at it is to use lasso to cut those variables out, then do your stepwise, and then look at if you still think that there's covariance in your data and it's not perfect, using ridge and other techniques, because sometimes you don't have all the data, you don't have a perfect model to work from. Lasso is actually used quite extensively for that variable selection technique I just mentioned, and in fact all the books, the first thing they say about lasso is it's used for that technique. You can see why this is powerful when it drops out the V4 completely from the model, but the linear regression would have, you know, carried on using that. Now, I still, even after all this, prefer the idea that you have to find the variables which are collinear and pull them out of the model and identify by hypothesis testing and different methods of graphing and looking at your data, so you produce the most smallest model you can do, the least complex, to avoid overfitting. But I can accept that not always that's possible, and these are two useful techniques, and I hope you've seen that what they can do. To just reiterate, the function, if you want to play around with them, is glnnet, and you know, these are looking at the values that it gave the coefficient, and it's not showing the actual accuracy of the model. It's to say that a linear regression in these cases varied hugely, while these were a bit more compact and much more able to fit a model better when there was covariance and collinearity in the data. And what you can think about is ridge and lasso would produce, because of the variable was smaller, hopefully a more accurate model when predicting unseen data. Something for you to play with. As I said, I still think go and use other techniques to try and pull the wrong variables out, but that might not be possible. Thanks, and have a good day. Bye.